I hope everybody is fine and in this video I'll be basically applying time-dependent perturbation theory to a two-level system. And what I assume here is that the perturbation is sinusoidal in nature. And so time-dependent perturbation theory. And we have already discussed time-dependent perturbation theory. And what we have is we understand that in quantum mechanics, this time-dependent perturbation theory is basically used to deal with systems where the Hamiltonian of a system, the Hamiltonian gives us the total energy of the system. This Hamiltonian of this quantum system changes with time. Now, this method is particularly useful when the system that we have, when this system is subjected to some small external, if we have a system subjecting this system to some small external perturbation. I mean, also call it as an influence, an external influence, a small external influence that varies over time. Now, for the sake of simplicity, uh, if I have to write down the total Hamiltonian dependent on time, and if I write down that as h of t here in this case, it must be equal to h naught plus v of t. Where, as we understand, this h naught is the unperturbed Hamiltonian, and it's completely solvable system where we know the eigenstates and eigenvalues. We know the eigenstates and energies. And the next term is v of t, and this v of t is time dependent. So using time dependent perturbation theory, what we can do is we can compute this v of t. We can calculate it and 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 yield the transitions between the different quantum states due to v of t. So to proceed from here, this was a review of the perturbation itself. Now, what we have is we have a two-level system, as I said before, and and this two-level system is subjected to a sinusoidal perturbation. So if I consider this two-level quantum system with states as 1 and the ket of 2. And with these two states, we have unperturbed energies. And let's assume these energies are E1 and E2. Now, what we have a time dependent parameter here, and that time dependent parameter, because I'm choosing my problem as sinusoidal in nature and assuming that v of t is v naught cos omega t. And this is the perturbation that we are applying to this two-level system with the state 1 and state 2, and the energies associated with state 1 and state 2 are E1 and E2. So using the first order perturbation, first order time dependent perturbation theory, what we have for unperturbed Hamiltonian, which is H naught, I simply have this H naught acting on state 1, that is going to give me E1 state 1. And for state 2, I'm going to get E2 eigenstate 2. So these are my equations for unperturbed Hamiltonian. And we can see that the perturbation is sinusoidal in nature, the perturbation that we have been executing here. Now, as we know from the theory, as we have already discussed, the transition amplitudes using time-dependent perturbation theory, we would like to use that. So what we are trying is we aim to find the transition probability from the state 1 to the state 2 at time t. Now in first order time dependent perturbation, this transition amplitude, so we are moving to 2, so I'll call it C2 of t, is minus I by h bar 0 to t. The expectation, the matrix element of this, this is 2 v t dash 1 e to the power of I omega 2 1 t dash dt dash, where this omega 2 1 is nothing but E2 minus E1 by h bar. Absolutely. And this omega 2 1, what we call this is the angular frequency corresponding to the difference, corresponding to the energy difference between these two states, the state 1 and state 2. Now, another important parameter here we have is this matrix element. And what is this matrix element? 2 v of t dash 1. So this is nothing but v naught cos omega t dash. And so we can use this perturbation term in our integral, and what we will get this C2 of t is minus I by h bar integral 0 to t. And for this matrix element I'm going to use, I think v naught should come out, then cos omega t dash, then e to the power of I omega 2 1 t dash dt dash. That should be the case. So this is my equation, and I can think of cos theta. What's cos theta? That's e to the power of I theta plus e to the power of minus I theta by 2. So I can use it for cos omega t dash. So that is going to be e to the power of I omega t dash plus e to the power of minus I omega t dash divided by 2. That should be the case, and I can use this in my equation here. So for cos omega t dash, I will be using the result. So C2 of t is minus I v naught by h bar integral 0 to t, and here I have e to the power of I omega t. This is omega t dash, then plus e to the power of minus I omega t dash. And I think this 2 will come out, and then we'll have e to the power of I omega 2 1 t dash, and then dt dash. I think it should be clear up to now. So we can, what we can do is we can multiply, and we will have two independent integrals. So I can keep my I can keep my I omega v naught by 2h bar outside. Okay, so inside I'll have integral number 1 0 to t, then I'll have e to the power of I can think of omega 2 1 and then plus omega times t dash. Okay, and then it will have dt dash, then plus integral 0 to t e to the power of I omega 2 1 minus omega, then t dash and dt dash. And then we can look for the integration, and this is an exponential function. The integration of exponential function is the exponential function, but you have to divide it by the internal derivative of its exponent. So in this case, the internal derivative will be iota omega 2 1 plus omega. Okay, when you'll give the upper limit and lower limit, for the upper limit you will have the function, for the lower limit you will have e to the power of 0, so e to the power of 0 will give us 1. I think that should be clear. So the result is obvious. What we'll obtain here is, we will obtain this C2 of t will come out to be minus C minus I V naught by twice h bar, and once we integrate it, what we will get is e to the power of I omega 2 1 plus omega times t. This is our upper limit, divide by iota omega 2 1 plus omega. This will be for the first term. For the next term we will have, okay, I forgot to write down, the lower limit is minus 1 here. Okay, then you will have plus e to the power of I omega 2 1 minus omega, and then t. Okay, this is our upper limit, minus 1 divided by I times omega 2 1 minus omega. So closing. So the integration is gone. That's right. So this is our exponential divided by the internal derivative of the exponent, giving the limits. For the upper limit, you replace t dash by t. For the lower limit, we will have e to the power of 0, and e to the power of 0 will give us 1. So so this will be our C2 C2 of the transition probability that we have been looking for. Now, the transition probability that we have, the transition probability, that's P from 1 to 2, that is simply C2 of T whole square. No need to revise it, it's understood. And for time t, for the time t to be large compared, if I assume that t is very greater than that of 1 by omega 2 1 plus minus omega, what we will have, the rapidly oscillating terms in this equation will average out, and we will get the result. What will be the result? The result will be P from 1 to 2 as a function of t, as a function of t will nearly come out to be v naught square. Here you should see this iota will go. This iota will go. So v naught square 4h bar square, and then you have the exponential function, and you can write it in terms of sines, and we will have the result as sine square of omega 21 minus omega times t divided by omega 21 minus omega whole square. This will be term number 1, then plus sine square of omega 21 plus omega times t divided by omega 21 plus omega whole square. And this is what is our transition probability from the state 1 to the state 2. So we have been talking about this transition probability, and we would like to focus on this result that we have obtained here. That should be our state of argument, which we would like to go with and to discuss. Now, the very first, I think it's better to repetize this equation. So what I have p1 to 2, and this is v naught square by 4h bar square, and then we have this whole thing sine square omega 21 minus omega times t divided by omega 21 minus omega whole square, then plus sine square of omega 21 plus omega t divided by omega 21 plus omega whole square. All right. Now, when the perturbation frequency, so what is our perturbation frequency here? Perturbation frequency, that is obviously omega. This is something that's coming from the external to disturb the system. When this omega is close to omega 21. So what's omega 21 is basically the natural frequency of the system. This is the natural frequency of the system. So you have a case when this omega is close to the natural frequency omega 21. The terms that we have, like omega 21 plus omega and omega 21 minus omega, they behave differently. These two terms we can see here in this equation, these terms behave differently, and we want to talk about that behavior. Now, the first argument is off-resonant term. Off-resonant term. Now, what's that? The term that we have here, omega 21 plus omega, what it does basically, this omega 21 plus omega, it represents a frequency that's basically far from the resonance. It's taking the system away from the resonance. And this term oscillates fast. It oscillates fast. Or you should say rapidly. This is rapidly oscillating. And since it oscillates fast, it averages out to 0 over the time. So this term does not contribute significantly to the transition probability that we have obtained here. So this is our off-resonant term. That's omega 21 plus omega. And talking about the next term, what's that? That's omega 21 minus omega. omega 2 1 minus omega. Now this term corresponds to resonance condition. It corresponds to resonance condition, where the frequency of the external perturbation that that we have omega, this omega matches, it matches the energy difference. And what's that energy difference? Omega 2 1. And in this case, the denominator that we have here, this denominator becomes small. And if the denominator becomes small, the amplitude of the transition, the amplitude of the enhanced transition grows. It grows significantly. And this leads to that enhanced transition probability. So, so, so omega 2 minus omega 1, what leads to the resonance condition, leads to the transition probability. And thus the resonance occurs when this omega is nearly of the order of omega 2 1. And that's what it means, is that when the perturbation frequency, that the perturbation that we have utilized, when its frequency matches the energy gap of state 1 and state 2, that's E1 and E2. Now, so what we observe here is that we have a sinusoidal behavior. And that's clear from the equation. We have a sinusoidal behavior. Now, the transition probability, what happens to it at resonance, it grows with time and follows this sinusoidal pattern that's governed by this equation. Because the system is being driven by the time-dependent perturbation. That's an argument. So if I write down this transition probability from 1 to 2 as V naught square by 4h bar square sine square omega 2 1 minus omega times t divided by omega 2 1 minus omega whole square. This formula that we have, it tells us several things, several important things that are happening to the system. What are those things? The first thing is, it tells us the transition probability oscillates. This transition probability oscillates between the state 0 and a maximum value. And a maximum value. As a function of what? As a function of time. The sine function that we have here, it captures the fact that the probability grows and then shrinks, and then grows and then shrinks, and showing that periodic nature, reflecting the coherent nature of quantum transitions. And for omega equal to omega 2 1, the value of this thing will be equal to 1. If we think in terms of limits, as sine theta by theta, theta tends to 0, this term is going to give us 1. What does that mean? That means the probability grows maximally. This is the point where the energy from the perturbation is efficiently transferred to the system. And the oscillatory behavior that we have, this oscillatory behavior is related to Rabi oscillations. Which we have seen in two-level quantum systems. When they interact with an oscillating external field, the Rabi oscillations describe basically how the population of the states oscillate back and forth between state 1 and state 2 over some period of time. Now, what could be the physical interpretation of the thing that we have come up with till now? We have the off resonance, and off resonance is a condition when omega is far. It is far from omega 2 1, and the transition probability is very small because the system cannot efficiently absorb the energy in that case, the case that we talked about here. And so this is what is our off resonance that's occurring due to omega 2 plus omega 1. And when we go close to the resonance, that means omega 2 minus omega 1, omega 2 1 nearly equal to omega 1, the transition probability grows. It grows, peaking at omega equal to omega 2 1. And if we think for the long time limit, for a long time, this P of t becomes significant only near the resonance. At resonance, the system undergoes a transition. So it's the resonance that causes that transition from the lower state to the higher state. And this explains basically why in many quantum systems only certain frequencies, those matching the energy difference between the two energy levels, will induce the transition. It's not all the frequencies will cause the transition. Only certain frequencies will cause the effective transition. This is basically the basis for spectroscopic techniques, where we probe systems with external fields and measure the transition to learn about these energy levels. So, with this, I would like to stop here. So this was the crux of the problem that we chose as an application of time-dependent perturbation theory. So with this, I would like to say goodbye to all of you.